Hello, this is our 2013 Model S. I received this car in February of 2013. It was a very early Model S. I think $107,500. And I got it with these 21-inch turbine wheels. My wife mostly drives the Model S. I have fallen in love with the Model 3, and I think a big part of that is simply it's easier for me to get in and out of. I don't know if it's the height of the door opening or that the whole dash and door are moved forward in the car, but for some reason I seem to have a lot more headroom getting in and out of the car than I do in the Model S. I think that'll be improved with the Model Y, but I'm hoping to skip that one and go right to the pickup truck, which we don't know what it looks like yet, but pickup trucks tend to be much easier to get in and out of, which is why big guys seem to like big trucks, or that's part of it. You also sit up higher, have a little better visibility. But in any event, this has been a great car. I still love it. I bought it black. Shiny black cars are kind of in my wheelhouse. And these Turbine 21-inch wheels look pretty good in 2013. The Continental tires have not been a big impressive thing. We have about 22,000 miles on this 6-year-old car. But we're pretty halfway into the life of our second set of Continental tires. As I noted last week, I have procured some new wheels from a company called the new Aero. And additionally, at their recommendation, picked up some Pirelli Pzero tires. Now, both these Continentals and the Pirelli Pzero are 245 by 35 for a 21-inch wheel. One of our viewers in our last video alerted me that the 35 is not millimeters, but it's a ratio, a percentage of the width. And so it's 245 millimeters wide, and 35% of that, or about 86.5 millimeters, is the profile where the tire rises above the wheel. I stand corrected. Tires are not normally my favorite topic, but we are going to do some testing with these. The max pressure for these low-profile tires is a rather high, 51 psi, both for the Pirellis and for the Continentals. And Tesla recommends 40 pounds per square inch pressure for optimal operation. The guys at the new Aero make a kind of an interesting claim, and that is that they're 9.9% more efficient with regards to drag of the entire vehicle using their wheel, and as opposed to the Turbine 21-inch. Understand that I think the larger wheel looks great. I don't do a lot on track, so the low profile doesn't really help me there, but I just think it's a very good look, and so I got it. But I knew at the time that this sacrificed a bit of range on the car. And so I found it interesting that these gentlemen think they've engineered a wheel that might get me back close to the original efficiency, watt hours per mile, of the smaller wheels. And so we're going to go test these on the car in kind of their final day. We sent the wheels and the tires over to Campus Auto, one of your finer automotive garages here in the local area, to have the tires mounted on the wheels, valve stems put in, spun balanced, TPMS put in, and so forth. And then we will swap them out here on the car. So we're going to take the Model S out for a little drive. It has a pretty basic but somewhat interesting energy screen that will graph your power usage over 5 miles, 15 miles, or 30 miles and give you an average. And so we're going to take it out on Interstate 55, going north from Cape, a relatively flat, straight stretch, and set the cruise control to 70 miles an hour, and do 5 miles at 70 miles an hour, and see what our average watt hours per mile comes out to. I'm not too concerned about what Tesla calculates as the range. I want to know how many watt hours per mile I get in the car on that stretch of highway. And then we will exchange the tires and wheels and go do the same stretch, starting at the same mile marker and going fully at 70 miles an hour before we hit it, and do the same test with the new wheels and tires and see if there's really any gain. Some other factors that can come into play, I suppose, is the interplay with other vehicles on the road. We're going to accept that imprecision, but we do want the tire pressure has a great deal to do with rolling resistance. And so we want both sets of tires exactly pumped up to the same pressure and accurately done all the way around both times to try to eliminate that as one of the variables. And so we're left with the differences in rolling resistance in the tires, which could be substantial, and the drag caused by the wheel. And these guys are saying that the wheel moves 30% less air, and so creates an overall gain of 9.9% in drag on the car. Do I believe all that? You know, I've been proven wrong so many times it doesn't matter what I believe. We'll test it and see. I guess I don't think we're going to see a 9.9% increase in watt hours per mile, but we should be able to see something, and I'm interested to see what that is. And that watt hours per mile is not, it's kind of linearly a component, but it's not the defining component in the amount of drag created by the vehicle. But drag does play a large role, and it plays a larger role at higher speeds. There's going to be no difference in these wheels. At the 22 miles an hour, I normally dawdle around Cape Girardeau in. But at 70 miles an hour on a road trip, which is where range becomes an issue, it'll be interesting to see if there's any gains to be had there. So stay with us. We're going to go for a drive and record what our watt hours per mile are with the original wheels and tires. So here we are in the car, and this is the screen we use for efficiency. We can set that for 30 miles or 15 miles or 5 miles, and we're going to set it for 5 miles, and it will show our energy usage for that 5 miles and do an average watt hours per mile. We don't really care about the range. And so we're going to go out on the freeway and get to a specific mile marker where we will set this up and record 5 miles, where that gives us the entire graph and our average watt hours. Just past the 100 mile marker on this road, we're going to go up a little hill. We have some trucking ahead of us, and doing about 65. Busy day here on Interstate 55, and so we're going to have to do our test at 65 miles an hour instead of the 70 I had hoped. And we're going to do 5 miles, hopefully without having to touch the brake or the cruise control, at a steady 65 miles an hour for 5 miles. And there's 101.2 mile marker. Right now we're averaging about 310 on the 5 mile scale, and it's dropping 291 at this point. This is a little stretch of road I've done a lot of testing on. It's straight, not entirely flat, but it's a pretty good test stretch and handy to the shop and so forth while I'm getting this out on the freeway for a few miles of run. Down to 276 on the average. 102.6 mile marker. Cresting a hill here. Oh, great. I'm catching a little raft from an ass clown hauling a tractor. .65 seems to be about what we're doing in this lane. They're passing some in the left-hand lane. We might get a little faster, but we'll also get into the action over there. Down to 262 watt-hours per mile. And we have Fruitland Jackson in 1 mile. We're at 104.6. This is all going to work out. And over the last 5 miles, 104.8. And there is 105.0, and we have 249 watt-hours per mile on that drive. Of course, we have the windows up, and we're taking it off cruise here. I'm going to get off of Fruitland Jackson exit. So 249 watt-hours per mile seems to be the 5 mile graph at 65 miles an hour. We're at 105.0. Can we get her up to 70? Oops. And we're at 70 miles an hour. See how this goes. Going down to, now we're at 70. Go down to 100.0. See what that does. At 70 miles an hour. And of course, from Cape Girardeau to Fruitland, it's uphill both ways. Yeah, we got a big goose there. We gotta get that out of the picture. I'll wave for him. Of course, we saw our acceleration up the ramp, which is fairly dramatic. We didn't have that coming in here. We're going to have to go far enough to get that out of the picture. Pickup truck and have another one creeping up on our other side and let him get around. We're going to switch lanes, see if we can maintain our 70 miles an hour. And there's 100.6. 291 on that leg. Well, here we are. We got the new shoes on. Comparing the weights, the turbine wheel, which you see there, is 58.6 pounds with a wheel and tire and stem. And these were 59.8 for the new Aero wheel and the Pirelli tire. And that's without the stem. So about 1.2 pounds heavier with the black matte Razor wheel from the new Aero and the Pirelli tires. Right now, Zeke's filling the tires to the precise 40 pounds we used in our test yesterday, and we're going to take another ride. I don't know what I think. I thought I really like these black wheels and tires, but you know, I can't really say I've decided which is prettier at this point. But these are newer, and we're going to take them on a test drive, see if there's any difference in our watt hours per mile, and just what we're talking about here with the black matte Razor wheels and the Pirelli Pzero tires. Stay with us. Are we on and running?
Yes.
Okay, here we are on the new set of Pirelli Pzeros with the new Aero matte black Razor wheels, and it just feels a lot smoother to me already. I see what Uli was saying about nervous turbine wheels. These just don't feel that way. We're at 65 miles an hour, which will duplicate our drive yesterday with the turbine wheels. And we're going to start measurement at the 100 mile marker and go at 65 to mile marker 105 and see what our average is. Yesterday it was 249 watt hours per mile in the 65 mile an hour segment, and we did about 279 on the 70 mile an hour segment coming back. And there is 100.2, so we're off and going. On our graph, we still have accelerations coming onto the freeway and so forth, so we're at about 434, but dropping our average as we cycle through. We're going to get a good 5 mile run at exactly 65. I think that will do it. We did, I forgot to mention, in changing the wheels, also put the Tesla logo caps. Were easy to transfer to the new Aero wheels, and they look pretty good. They're kind of a silver cap, but in the middle of a black wheel. That looks pretty nice. I may try to get some of those white on black caps from Tesla. I saw some in their story the other day. Ordered their hub, their fob that they now have for the Model 3. I should be getting that in today or tomorrow. And we're cruising at 65 very smoothly. And this car seems a lot calmer at 65 using the new wheels and tires. In fact, 65 feels quite slow this time. Perhaps we don't have as much traffic as yesterday, although we seem to be getting some cutting in front of us. I hope they don't cause us to have to break our pace here. It's important that we don't do any decelerations or accelerations except for the normal elevation changes, which are minimal on this stretch and very gradual. But that's why we're the same stretch of highway that we did yesterday under pretty much the same conditions. Same people in it, 40 pounds PSI in the tires. But using the new tires and wheels. See how we compare. I was a little disappointed. We're about 1.2 pounds heavier per wheel and tire. The new Aero setup, but that's pretty minimal difference. That's 105.0 and 317 watt hours per mile. That is strange. We have actually lost efficiency somehow from yesterday to today. And we're going to get off here at Fruitland. What could account for that, Danu?
Not sure.
You and I are about the same size we were yesterday.
Yes.
We don't have the heat on or anything, do we?
I don't think so. No, it doesn't look like it.
We're at 75 still on the temperature dial. Don't have any seats going. But that's very strange. See what it does at 70 on the way back. I think we measured to mile 99 going back at 70 miles an hour. 94.8. On this stretch, we're going to go from 104 to 99 on our graph. And what was our number coming up?
I believe it was 330, was it?
Check the video. We seem to be doing better here. Even the big acceleration spike moving across it. cost us 19 watt hours per mile for the new wheels. They not only didn't improve it, they seemed to disimprove it. Or degrade our efficiency on the road with the same tire pressure and the same two guys in the car, the same speeds, and exactly the same terrain. Okay, we're back, and after reviewing the videos of the tests, we have some surprising and indeed inexplicable measurements. Not sure what was wrong with our methodology. On the northbound phase, we started our measurements at mile marker 0 and or 100, and finished at 105. That's a 5-mile stretch as measured by the Missouri Highway Department. And that matches our 5-mile range on our average. At 65 mile an hour, we did 247 watt hours per mile with the turbine wheels, and with the Razor matte black wheels from the new Aero and the Pirelli tires to the same 40 psi pressure, we did 317 watt hours per mile. That's an increase of 70 watt hours per mile using the Razor tires. So if they're more efficient in the wrong direction. On the southbound leg, a little better. We went from mile marker 104 to 99, going in the southbound direction, and at 70 miles an hour. With the turbine wheels, we got 291 watt hours per mile, and with the Razor matte blacks, 314, which is about 23 watt hours per mile greater use using the Razors. And so in both directions, the Razors were a loss of efficiency. It took more watt hours per mile to cover the exact same highway territory, and at 65 and at 70 miles per hour. It was closer at 70, and who knows, it might be even the same at 80, but 80 is illegal here. And so Uli Heckman of Munich, who is part of the team in Sweden, developing these wheels, was touting some better efficiency, and I can't find it, if it has any. Finally, Uli was also very specific. I asked 3 times about the tire pressure monitoring system, and he assured me that the local tire shop could just put in any TPMS and then it would be fine, and I wouldn't have to do anything. Turns out there is a reset screen in the car to reset the TPMS, but it doesn't work with whatever TPMS they put in at Plaza or at Campus Auto. The one they did put in was a 315 433 megahertz dual unit that you can switch back and forth between the two. I understand the early Model S from 2013 uses the 315 megahertz, but it doesn't use this one. And so we still have to do some research, and the tire pressure monitoring system has turned into kind of a shit show over something very minor. We're going to wind up with some effort just to get it to work with this car. So $7,000 worth of wheels and tires, and tire pressure monitoring systems, probably $200 or $300 just to have them mounted and balanced and all that done, stems and TPMSs. And our TPMS doesn't work, and we actually lost efficiency. But it's the consensus of almost everyone in the shop that it's a better looking wheel. So some bling. It's always better to look good than to be good. And in this case, I'm afraid that's what we have. So I would have been delighted to report a huge gain in efficiency in watt hours per mile. We don't see it. I don't know anything we could have done to make it a more straight up comparison. And as far as the TPMS, that's a shit show that is not even resolved yet and probably won't be for several trips to campus and perhaps to Tesla. So I'm a little disgusted with the tire pressuring monitoring system because I did make a point about asking about that, and he assured me in all confidence that it wasn't a problem. It's a problem. And so, kind of a fail going on here, except for the part that, I've decided I like these wheels. They look pretty good. They feel better. Well, any new rubber always does, though. And these new Pirelli tires feel pretty grippy. And it feels a little more secure. That's a very subjective measurement. I would say it's not a measurement, it's a feel. And I would note that every time I put new tires on a car, it feels better. Maybe it's just because my wallet's a little lighter, and so we don't have as much weight in the car. But for some reason, I always celebrate new shoes. They just feel better. And so that's probably what's going on here. So not everything we do at EVTV works out. And this one looks like a big nothing burger at best. Except it's pretty. The switch of the Tesla caps to the new Aero wheels was uneventful and no particular problem. And I think it looks pretty good. Stay with us. Solar is getting to be a lot more fun than I thought it might be. You just can't ask for more help than the utility grid companies of the United States. They're starting to make me look like a hero, and just 2-3 years ago, I was looking like a madman. Well, it's getting better. This week, of course, as you know, Pacific Gas and Electric, which is involved in a $10 billion lawsuit, is turning off power to a number of customers in Northern California. There is no wildfire, but there might be because the winds are blowing 25 to 35 miles an hour. And it is kind of dry, as it gets this year every time. And that's why they have wildfires out there every year anyway. But 2 years ago, they had one that was quite damaging, and there was a lot of property loss. So today, they are preemptorily and preventively shutting off power to up to 800,000 customers. That's a couple million people of humanoid species, just in case. And I think that's just in case they lose the lawsuit. But they say it's just in case of a wildfire. I can't, and that's for periods up to 2 weeks of loss of power. Now, for most businesses, that could pretty much end your business. For most homeowners, it's very inconvenient. Life without electricity is kind of an adventure for the first 2 hours, and after that, it sucks really hard. I watched a video of a guy on a motorcycle with a 5-gallon can going to his local airport to drain Hunter low lead out of the wings of airplanes to power his Honda 2200 generator. And he interviewed a guy in a sporting goods store who had sold 43 of those generators that morning. And so it just turns into a little bit of a shit show. So, I can't imagine such a crazy situation. I'm glad it's in California. However, that's not the whole story. There's a much less dramatic story going on that this summer, San Diego Gas and Electric made a couple of changes to their tariffs. These changes are actually in compliance with California State Law 327, Senate Bill 327, which mandates, in one of the most astonishing bits of collusion between governmental regulators and the industry they regulate that I've ever been privileged and astonished to see, a couple of things. San Diego Gas and Electric has about 150,000 solar installations on their residential customer base, and they have increased their monthly connection charge from $16 to $40. So if you don't use any electricity at all, you still pay the $40. And introduced a fairly extreme version of time of use billing. And that time of use billing that they've introduced this summer is where you pay about 9 cents a kilowatt hour from midnight to 6 a.m. Now here in Missouri, our flat rate is 10 cents per kilowatt hour in the summer when our air conditioners are on, and 8 cents in the winter when they're not. San Diego is now getting 9 cents a kilowatt hour from midnight to 6 a.m., 29 cents an hour all other hours except from 4 p.m. to 9 p.m. They are charging 53 cents per kilowatt hour. That's about 5 times what we pay here in Missouri. I actually saw another YouTuber talking about survival techniques, and he had invented a very cunning trick to decrease your electricity use during that 4 to 9 p.m. time period. He advocates using a barbecue grill to cook dinner on. They're just not like back here in the States. So anyway, this is not indicative of things to come. This is things that are already here. The reason San Diego Gas and Electric was first is they have a smaller customer base and more modern and more sophisticated billing and accounting software in their system. Pacific Gas and Electric, much larger, and California Edison, larger yet. Well, they may be similar in size. Are intend, if they can master the software upgrades and changes necessary, to implement this by the end of the year. As California goes, so goes the nation, although I hope they do not emulate the preventative power outages to prevent forest fires here in Missouri ever. But the time of use and increasing rate charges, now that that's established in California, will be a model for the nation and for the utility grids to implement that, pointing to California as they're a few years ahead of us on solar installations, and this is what they've worked out. And they'll no doubt get that approved in most places, although Massachusetts is kind of going the other way. And Florida, after having a big ruse scam pulled on them during an election in 2016. Those people down there are pretty militant. I'm not sure that this will quite reach Florida. They're mad about it, and they're aroused, and it has been tough on the politicians down there. So time of use is kind of a thing. I was going to put together a system using a Connext grid-tied inverter and that, and kind of decided to just stick with selfish solar, but kind of a modified selfish solar for time of use. Our inverter is an inverter charger, and normally we would run it in one of the two available modes, battery priority or AC grid priority. And we would run it in battery priority, at which point it would only switch in the grid with an internal transfer switch in the event the battery got low. And when the battery got back up, it would switch to AC back to battery operation. It does have another mode, and that's AC priority. And that's where it operates pretty much as a standard UPS. And so if you have grid coming in, it passes it through the transfer switch and to the output. And it will also charge the batteries from that, but once they're full, it pretty much runs on the grid, and it only switches to battery after the loss of grid power, about a 10 millisecond delay. And so it occurs to me that there's kind of a cunning thing we can do here, in that if we had an external switch that we could control, we could apply grid power to the Signir inverter, leave it in AC priority mode as full time, but apply AC power to that system using an external switch. Well, why can't I just do that with the transfer switch in the Signir? Well, I should be able to, but of course I can't. And philosophically, this is one of the central problems I've got with equipment as it is. With a battery, you should have the intelligence to control the system with the battery. It's been built into inverters, and so they wind up having to know about 20 different kinds of batteries. The battery only needs to know about one kind of battery, and the inverter, which is really not necessarily a very intelligent device, all it needs to do is convert DC to AC, should do what the hell it's told to by the battery. But that's not the architecture that has emerged. It's been inverter-centric, and everything is seen as adjunct ancillary equipment around the inverter. I think the correct model is the battery is the center of the system, and everything around that is an auxiliary equipment. But you know, they didn't call me on this, and so they've already got it done. And so the Signir doesn't operate that way. I negotiate with these people for months for very minor changes and things, and it's tedious. But the technique I'm going to show you would pretty much work with just about any inverter, because almost all of them have a UPS backup mode. Since we charge primarily from the photovoltaic panels anyway, and this, in fact, will work with almost any inverter. They don't tell you this, half of them don't know it, but the other half are actually starting to tout it, and they're actually using my terminology of AC coupled, which used to mean something else, to talk about charging the batteries for microinverters on the roof. So if we leave it in AC priority mode, and we have an external switch to apply AC to it when we want, and not AC to it when we don't want, we can switch back and forth between battery-powered inversion and AC pass-through all we want. And in fact, that's what we've done here with our switch box. This is just an ordinary knife switch box, UL NEMA enclosure with a switch. But we've mounted in here a couple of kilowatt contactors and an LED. And we're using our heat enable output to turn that on or turn it off. And we've been doing that when we have excessive current or power from our panels. We've got 38 kilowatts of photovoltaics and a 15 kilowatt inverter. If it gets out of hand, it automatically turns on the AC power, and we've been using it as a dump load, actually, to dump our excess power to the grid. Got something else in mind, but that's how we built that. It might be a little overbuilt. This is a $79 Chinese relay. It's not precisely a contactor. These contactors are built for making and breaking DC voltages, which causes arcing, and so they're gas-filled, have magnetic blowouts, all this stuff, and that's what makes them expensive. This is about 79 bucks, but it's simply a simple relay with kind of heavy contacts to carry 100 amps because AC voltages have a sine wave, and so a crossover point 60 times a second. So if you make or break, it's not going to arc anyway. So this is a $79 relay. It has a 12-volt coil, and so we can run it with the same heat enable output. This is a little more complicated, but I kind of like it because it's sort of industrial. And it's not really built for this purpose, but it's kind of good for it. It's a Generac automatic transfer switch, about $450, which, believe it or not, we're pretty close to that on this little build. This has an output and two inputs, one for the AC grid and one for a generator, and two solenoids that work on 240 volts AC. The nice thing about it is it has a transfer input on the controller that 12 volts will cause it to switch over. And so if you lose your AC grid, another signal turns on your generator, and when it's stable, it does this transfer signal, just a 12-volt signal, and that causes it to switch over to the generator. If you get the grid back, you can turn off the generator and it'll switch back. We could just use this for a switch to switch the AC. We've got to do a couple things, put a relay to switch 240 to the lower solenoid because we're not going to hook up a generator, and of course make connections with our for the transfer using the same 12 volts. And we would probably add an LED as we have here that tells us if we've turned it off and on. So that's the concept. Now what we need is a clock. Well, our battery controller actually gets a very good clock from the NTP, National Time Protocol server at the National Institute of Science and Technology in Boulder. I don't know exactly where the server is, but the time signal comes from NIST, and so we can get the exact time and date with our controller. Now, you have to have a Wi-Fi hub for us to connect to, which you need to have a display anyway. And that hub has to be connected to the internet. Doesn't have to be a fast connection. Doesn't have to be a very good connection. We're not going to get very much data, but we're going to get an NTP time signal. And so that lets us set our clock. So what we need to do is use our heat enable output based on a clock to switch the AC grid to our inverter while it's in AC priority mode. And in this way, we could, for example, switch to AC at midnight. We don't even need solar panels for this, by the way. Just our PowerSafe 100 or PowerSafe 60 and an external switch. We could turn on the grid at midnight and charge our batteries until 6 a.m. And then we could leave the grid on if we wanted to until 4 p.m. And we cut off with our external switch the AC grid. And now the batteries come on and provide all the electrical power from 4 to 9 p.m. And then we can switch back to the grid or wait till midnight and switch back to the grid. So this would be a kind of a time shifter for power in your location, whether you had solar panels or not. Now you could do this otherwise, and this is probably what we'll do. Well, it is what we'll do here because we don't really have time use, but you'll get the idea. We'll turn on the grid at 10 a.m. I'm pretty much full anyway. My batteries are pretty much full. And we will let the solar panels charge the batteries until 4 p.m. and then switch and that would be on the grid. Now, it's using the grid to charge the batteries, but not really, because it's passing the excess power through from the solar panels, and it gets to the charge circuit first and charges our battery, so any that's left after that is pushed out to the grid. So we'll do that from 10 to 4, say, and then from 4 to 9, we could cut off the grid and simply run on the batteries. And so the possibilities are kind of endless. It has required a major change to our software. Let's take a look at that. Okay, we have our software here. A couple of things to mention, possible welded contactor. I'm doing this on a bare board without the install. But as you can see, we have a Wi-Fi status. We are connected to our local access point, River House, as this IP number, and with a signal strength of minus 63 dBm. And we have retrieved our time mark from the national time pool, the network time pool, and we are running version 2.0. Let's go to our config screen. Let's see here. And here we are. Notice that we have our high temp set to 0. We're not going to use the heat enable for our temperature anyway. And so by setting this to 0, we're signaling the software that we're going to be using a schedule to switch an AC relay or contactor to apply grid power to our inverter. And if I hit the right arrow again, we get that screen. And again, we have our software version and the date and our Wi-Fi status, so we can tell that's on. We have AC grid scheduler is activated. If I go down and press an A and enter that, it's deactivated. And if I enter another A, it's activated. So I can toggle that on and off with an A. Right now we have the grid input is currently switched off, and I'm going to enter a grid all command, GRID all equals on, and as you can see, we've all gone on. These are AC grid time 00 is midnight, 1 a.m., 2, 3, 4, 5, 6 a.m., 7, 8, 9, 10, 11. This is noon. 16 is 4 o'clock. 21 is 9 o'clock. And then through 11 o'clock. And so we have all 24 hours of AC grid time. And on indicates our heat enable output will be activated or enabled, and that should close our relay or contactor applying AC to the thing. I can go to grid all equals off, and they immediately all go off. And so if I wanted to turn on the grid from midnight to 6 a.m., I would have to say grid on equals 0, and that comes on. Grid on equals 1, and that comes on. Grid on equals 2, and that comes on, and so forth. And so it's a little bit tedious to, but that would, and then at 6 a.m. It would go off. Now this activates at the top of the hour. So at midnight, we're going to switch on, and at 6 a.m., just as it turns 6 a.m., we're going to switch off. So these are top of the hour activations. You need to be aware of that. And right now it's 11:22. So let's say grid on equals 11. And by golly, here's where we show our AC grid input is currently switched to on. This is the indicator for the status of our heat enable output. And so this is how we activate it, and here's how it indicates on and off. And here is the schedule where that will happen. And it'll happen once you set this. It's stored in non-volatile RAM, and so the next time you bring it up, your schedule will still be there, and you'll still be activated, and you'll still have high temp set to 0, and so each time you apply power and bring it up, these will be applied until you change them. And so in this way, you can set up a schedule of what hours you apply grid power to the inverter and what hours you remove it. And by having the inverter set to AC mode, whatever that means on whatever inverter you're using, set up the inverter to be an uninterruptible power supply that comes on when the grid fails. And so by using an external switch, you can turn that on and off. And with this 2.0 update, we provide this schedule where you can use the heat enable output to switch the grid to your inverter or remove it from it. And when you remove it, it'll of course revert almost instantly, in less than 10 milliseconds with the Signal to battery operation. Now when you apply the grid on our particular inverter, it gives it 15 seconds to stabilize because it might be a generator. In this case it isn't, but the Signal doesn't know that. So it will delay 15 seconds and then close the relay and internally and start passing the grid AC through the inverter to the loads. And if the batteries need any charging, it will charge it per the settings you have on your inverter. And so that's how this works. And I think it provides a solution for time of use billing using almost any inverter, but certainly our SDG&E. If we go back to this one, we're using the charge enable output to do our frequency shift. And that's going to use the cutoff voltage. It doesn't really use the resume voltage. It uses the cutoff voltage. When our battery reaches that, we do a frequency shift to shut down the microinverters. And as long as these are the same, actually, we have to set resume to the same thing. I don't have that here. For now, it'll do it. If I set resume and cutoff to the same voltage, we can use that charge enable output to do our frequency shift at the cutoff voltage. Well, they're both the same voltage. It'll do a 500 millisecond frequency shift on the SDG&E inverter, and that will shut off our thing. So we can use these together, use the charge enable output for frequency shift, and by setting high temp to 0, we can use our schedule on the output there for the heat enable output to control our external relay or contactor. And so that's the update on 2.0. So that's pretty much the description of the software upgrade. Now we have a calendar you can fill out at least to the hour level, where at the top of each hour it checks to see if you want the grid on and off. And we can use that heat enable output based on that scheduler to switch our relay, our Generac, or this, and achieve control over our battery system, and whether we're using AC or battery 24 hours a day. And I think that's going to be important to a growing segment of our viewership. And I think we can make that work. It did take a bit of code to make that happen. But I believe that level of control is necessary, and the only way I can figure out to do it is with an external switch. And so you'll have to build some kind of a box like this, contactors, relays, or I like this Generac. It's kind of built for this, a couple of modifications, add an LED, a relay, do a little wiring in there, and this would be a dandy AC switch. It's rated for 100 amps. It's $452 on Amazon, and it's already put together. Like I say, you'd have to add a couple of minor things, a little ice cube relay and a LED and so forth, but fairly trivial. And we're now including the software to make that switch in our PowerSafe or version 2 controller, which has a clock. And so that's kind of the next step in the evolution of our controller for the Tesla Model S battery systems. And I think it's kind of a simple one, but it's I think going to be important going into the future in this conflict between the grid utility operators and what you want to do with electricity in your home. The beauty is it's all on this side of the meter. Now, not everybody can do this. Our equipment's not made to run by people who use refrigerators. You are going to have a little bit of do-it-yourself inventiveness and a familiarity with electronics. Our stuff just isn't going to work. We're kind of still dancing with the same people that brung us, and that's those who can go in their garage and change the world. And we're trying to enable them to do that. I think this solar battery concept is an important one going forward for them to work on. And at this point, if you want an electric car, I'd buy a Tesla. Stay with us.